Have you ever seen a robotic arm suddenly freeze or move in an unexpected way, even though its program seems correct? This often happens due to something called a singularity, a critical configuration in a robot's movement. When a robot reaches a singularity, its Jacobian matrix loses full rank. This means that the determinant of the Jacobian matrix becomes zero, and consequently, its inverse becomes undefined. This mathematical breakdown has significant implications for how the robot can be controlled. The Jacobian matrix serves as a fundamental link between a robot's joint velocities and the velocity of its end effector, which is the tool or hand at the end of its arm. It essentially maps the robot's internal joint movements to its external task space movements. At a singularity, the robot temporarily loses one or more degrees of freedom, meaning it cannot move its end effector in certain directions, regardless of how its joints move. The Jacobian's loss of full rank signifies that this mapping is no longer one-to-one, and it cannot be inverted to determine the necessary joint velocities for a desired end effector motion. Imagine trying to use a map where multiple streets lead to the same point, but you cannot determine which street to take to reach a specific destination because the map has a corrupted section. Engineers use this understanding to prevent robots from entering singular configurations. By calculating the determinant of the Jacobian, they can predict and identify these points in a robot's workspace. This allows them to design robot trajectories that actively avoid singularities, ensuring smooth and predictable operation. It is also crucial for understanding the limitations of a robot's operational envelope, particularly near joint limits or during self-collision scenarios where the robot's arm links might interfere with each other, leading to a loss of dexterity. A key concept related to the Jacobian at singularities is the manipulability ellipsoid. This ellipsoid visually represents a robot's dexterity at a given configuration, showing the range of end effector velocities achievable. At a singularity, this ellipsoid collapses in one or more dimensions, indicating the loss of motion capability. Another related measure is the condition number of the Jacobian, which indicates how close the matrix is to being singular. A high condition number suggests the robot is approaching a singular configuration. Ultimately, understanding what happens to the Jacobian matrix at a singularity is vital for designing robust robot control systems and for planning efficient and safe robot movements. By recognizing these mathematical breakpoints, we can ensure robots operate effectively without encountering unexpected freezes or uncontrolled movements, leading to more reliable and precise automation.
If you love robotics, like, subscribe, and keep building with us.